Electric power generation is a foundational component of modern civilization. It involves converting various forms of energy into electrical energy through a process that utilizes power plants, generators, and numerous supporting systems. This video provides an in-depth exploration of electric power generation, including types of power plants, classifications by fuel and prime mover, and key generator components. Electric power generation involves transforming primary energy sources such as fossil fuels, nuclear fuel, and renewables into electricity. This electricity is then transmitted and distributed to consumers for residential, commercial, and industrial use. The importance of electric power generation cannot be overstated, as it is the backbone of modern infrastructure, powering everything from homes and hospitals to industries and transportation systems. Efficient generation methods and stable supply are crucial for economic development, technological progress, and national security. Classification of power plants are facilities designed to convert primary energy into electricity. They can be classified based on the type of fuel used, e.g., coal, nuclear, solar, or the prime mover mechanism employed, e.g., turbine, engine. This classification helps in understanding the source, method, efficiency, environmental impact, and application of the power plant. Classification by fuel type: fossil fuel power plants, comprising coal, oil, and natural gas plants, are the most widespread. Coal-fired power plants dominate in countries with abundant coal reserves. They work by pulverizing coal and burning it in a furnace to heat water in a boiler. The resulting steam drives a steam turbine connected to a generator. Despite high emissions, modern technologies such as fluidized bed combustion and flue gas desulfurization have improved their efficiency and reduced pollutants. Oil-fired plants use heavy fuel oil or diesel. They are often used as peaking or backup units due to higher operational costs and dependency on oil imports. These plants offer fast startup but suffer from lower efficiency and higher emissions. Natural gas plants are considered cleaner and more efficient. In simple cycle plants, natural gas is combusted directly in a gas turbine. In combined cycle gas turbine (CCGT) plants, exhaust gases from the gas turbine are used to produce steam for a steam turbine, significantly boosting overall plant efficiency. Nuclear power plants use enriched uranium or plutonium as fuel. The nuclear fission process releases heat used to convert water into steam, which drives a turbine. These plants offer high energy output, low greenhouse gas emissions, and base load reliability. However, they involve complex safety measures, long construction times, and radioactive waste management. Renewable energy plants use sustainable resources. Hydropower plants use flowing water. Wind farms use wind turbines. Solar plants use photovoltaic cells or solar thermal collectors. Biomass plants use organic material, and geothermal plants use Earth's internal heat. These are environmentally friendly but often intermittent and location-dependent. Classification by prime mover: the prime mover is the component that converts thermal, kinetic, or hydraulic energy into mechanical rotation to drive a generator. Steam turbines are used in thermal coal, oil, nuclear, biomass, and some solar thermal plants. They require high-pressure steam and operate at high efficiencies when paired with regenerative or reheat cycles. These turbines are robust, reliable, and scalable. Gas turbines operate on the Brayton cycle. They are compact, capable of fast startup, and widely used in peaking plants and aircraft. In power generation, they are often combined with steam turbines in CCGT configurations for enhanced efficiency. Hydraulic turbines include Pelton, Francis, and Kaplan types, each suited to different head and flow conditions. These turbines convert the potential and kinetic energy of water into mechanical energy, which is ideal for both base load and peak load applications depending on reservoir capacity. Wind turbines use rotor blades connected to a gearbox and generator. Their output varies with wind speed. Modern wind turbines feature pitch and yaw control for performance optimization and grid stability. Internal combustion engines, diesel or gas, are used in small-scale or distributed generation, emergency backup, and isolated grids. They offer quick response and ease of installation but are less efficient and have higher maintenance needs. Nuclear power generation is based on controlled nuclear fission. Uranium-235 and plutonium-239 are common fuels. In a reactor core, fuel rods undergo fission, releasing neutrons and energy. Control rods made of cadmium, boron, or hafnium absorb excess neutrons, maintaining criticality. The heat from fission is transferred to a primary coolant. In pressurized water reactors (PWRs), the primary loop heats water under pressure, preventing boiling. This transfers heat to a secondary loop via a heat exchanger steam generator. In boiling water reactors (BWRs), water boils directly in the reactor core to produce steam. Advanced reactors include fast breeder reactors, which produce more fissile material than they consume, and small modular reactors (SMRs), which offer scalable, safer solutions. Nuclear plants require strict safety systems, redundant cooling, containment buildings, emergency shutdown systems (SCRAM), and monitoring systems. Spent fuel is stored in cooling pools and then transferred to dry casks or reprocessed. Despite high initial investment and social concerns, nuclear plants offer stable, low-emission, high-capacity electricity ideal for long-term energy security. Fossil fuel power generation, coal power generation involves complex processes, fuel handling, combustion, flue gas treatment, ash handling, and waste heat recovery. Supercritical and ultra-supercritical boilers operate at high pressure and temperature for better efficiency. Natural gas plants are favored for their flexibility and reduced emissions. In open-cycle gas turbines, the thermal efficiency is lower 35%, but in combined cycle operations, it can exceed 60%. Environmental control systems include electrostatic precipitators, baghouse filters, flue gas desulfurization (FGD), selective catalytic reduction (SCR), and carbon capture and storage (CCS). Economic factors, fuel price volatility, and decarbonization policies affect the long-term viability of fossil fuel plants. Transitioning to cleaner technologies and retrofitting older plants is critical for meeting emission targets. Hydropower generation. Hydroelectric plants use dams to create reservoirs, controlling the release of water to generate electricity. The plant consists of intake structures, penstocks, turbines, generators, and tail races. Control gates regulate flow, and surge tanks mitigate water hammer effects. Francis turbines are used for medium head and flow. Pelton turbines are for high head, low flow sites. Kaplan turbines are adjustable and suited for low head, high flow rivers. Pumped storage plants serve as giant batteries. During low demand, surplus power pumps water to an upper reservoir. During peak demand, water is released to generate electricity, aiding grid stability and frequency regulation. Environmental concerns include fish migration, sedimentation, and ecological changes. Mitigation strategies involve fish ladders, sediment flushing, and environmental flow releases. Generator components. The stator is the stationary part containing the armature windings. Laminated electrical steel reduces eddy current losses. Slots hold copper conductors insulated with mica, epoxy, or advanced polymers. Cooling ducts are integrated for thermal regulation. Winding insulation ensures electrical separation between conductors and core. Insulation systems must withstand thermal, electrical, mechanical, and environmental stresses. Class F or H insulation materials are used in high-performance machines. Cooling systems include air self-ventilated or forced, hydrogen in closed-loop systems, and water in high-voltage stators. Hydrogen's low density reduces windage loss, and its high thermal conductivity enhances heat removal. The rotor carries the field winding. Cylindrical rotors 2 to 4 poles are used in high-speed applications. Salient pole rotors with projecting poles are used in low-speed hydro generators. Rotors are balanced and precision machined to ensure smooth operation. Collector rings and brushes deliver DC excitation to the rotor. In brushless systems, a rotating exciter and AC generator is used, with a rotating rectifier bridge supplying DC to the main field winding. Excitation systems regulate the field current. Static excitation uses controlled rectifiers and thyristors. Digital voltage regulators provide precise control, fault detection, and remote monitoring. Power system stabilizers (PSS) enhance grid stability. The automatic voltage regulator maintains constant terminal voltage by adjusting excitation based on load conditions. It ensures synchronization, reactive power sharing, and voltage support. Governors control the prime mover speed. They receive feedback on generator load and adjust fuel input or steam water flow. Mechanical governors use flyweights, electronic governors use sensors and microprocessors for precise control. Speed droop is the proportional reduction in speed as load increases. It allows multiple generators to share load without instability. A typical droop of 4 to 5% ensures each unit picks up its fair share based on capacity and operating conditions. In a generation plant, the governor is a critical control device that maintains system stability by regulating the engine's fuel, steam, or gas input to keep the generator operating near its nominal speed. When the power demand or load increases, the generator tends to slow down, causing a frequency drop. Instead of attempting to instantly restore the original speed, the governor employs a built-in mechanism known as speed droop. Speed droop is essentially a calibrated, proportional reduction in speed or frequency as the load increases. For instance, with a 5% droop setting, the generator's speed will decline by 5% from no load speed to full load speed. This deliberate behavior is vital in systems where multiple generators operate in parallel because it ensures that each unit shares the load proportionally according to its capacity. The droop characteristic prevents scenarios where one generator would otherwise fight the others in trying to maintain a precise nominal frequency, which could lead to overcompensation and potential oscillations or hunting. By allowing a controlled deviation in speed relative to load changes, both the governor and speed droop work together to distribute power evenly and maintain the overall frequency stability of the grid. This dynamic modulation not only simplifies the operation when grids are interconnected but also enhances the reliability and resilience of the power system during transient disturbances or significant load fluctuations. Electric power generation is a cornerstone of modern development, encompassing a wide array of technologies, fuels, and mechanical systems. From traditional fossil fuels to advanced nuclear reactors and clean renewables, each method brings unique capabilities and considerations. Understanding the principles, components, and control systems behind power generation is critical for ensuring energy reliability, economic efficiency, and environmental sustainability. As global energy demands rise and the transition to low-carbon systems accelerates, innovation and informed operation of power generation infrastructure remain more vital than ever.